Good afternoon, everybody. It's a pleasure to try. Today, I'm going to cover astronomy since the time of Thomas Gresham. That is my goal, basically. And to understand that, we probably have to talk a little bit about astronomy before Gresham in the 16th century. So let's just see how we can progress here. I'm going to say a little bit about astronomy and in the world of art. So there were some interesting thoughts about the sky. Maybe one of the best known is the fall of Icarus. You see the sun depicted here in great glory by Bruegel. And so and another interesting phenomenon that was widely looked at a long time ago, although it wasn't understood at all, was Halley's Comet. And so again, you see this depicted here in a beautiful painting from the 14th century. Halley's Comet's up there, the Adoration of the Magi. So, of course, it was just only realized many centuries after the first observations of Halley's Comet, actually, that it did reappear in a very systematic way. And in Oxford, here is Halley's Observatory, pretty crude. It's this room at the top of a house now used for student lodging in Oxford. And this is a medal, but you basically get the general idea of a comet, and Halley, of course, realized that it was going to, and he predicted when it would be seen next, and had found various historic evidences for the comet. Okay, so that again was a realization that there was some interesting irregularity in the sky that had not been known before. So art has also heavily leaned on astronomy and our understanding of the cosmos. Maybe the most mysterious part of the universe is the dark matter, which is most of it. It's a substance that we know is there from measuring its gravitational influence on stars, but we have no idea what it is, and it's inspired many artists, modern artists. These are just a couple of depictions of cold dark matter as viewed in the modern art world. Okay, so in here you see, it's interesting actually, in this one on the right, where you see art with showing many different frames, but the content of every one is black. In some sense, that's actually a theme of how we think about dark matter in the universe. It's in many different types of galaxies. They look very different, but it's in many, many places throughout the universe. And we're trying hard to understand it, but haven't got there yet. So again, to come back to not art this time, but one of the most beautiful images, I think, has been taken in astronomy. This is Earthrise on the moon, taken by a lunar experiment. The original version of this was done on the Apollo program, but this is a more recent probe with an amazingly beautiful vision of Earthrise from the surface of the moon. And of course, this will be the goal of one of the main goals of future space tourism. We all expect, we're looking forward now in maybe 20 or 30 years to having visits to the moon, around the moon. And this will be one of the great things, no doubt, one would want to see. That would be quite amazing. Okay, now let me take you back to the beginning of astronomy, the very first thinking about it, and how much things changed around the time that Thomas Gresham became interested in developing the public knowledge behind astronomy and many other things. So this shows you the original hypothesis about the motions of the planets, basically first detailed by Ptolemy, a Greek mathematician in the 3rd century. And what he realized is that when you look at the planets, because the inner planets are moving faster than the outer ones, they're close to the sun, more gravity, they overtake them and appear to go forwards and backwards at certain times. And so these retrograde motions of the planets have to be explained. And at the time of Ptolemy, there was a very strong prejudice that the only natural motions in the universe had to be in circles. And clearly, if you have circles, it's very hard to get changing brightnesses of planets and so forth. So Ptolemy said, well, maybe the circles are slightly off-center, and that helped a little bit. But then it became clear that one needed to have circles within circles. That is, the planet had to go in a small circle, the center of which went around a big circle. We call these epicycles. And so Ptolemy then developed this idea of epicycles to explain the bright changes in brightness of the planets. There are apparent occasional backward motions in the sky when they overtook a more distant planet, and then etc. And so that stayed there. But as observations got slightly more precise, the epicycles got more and more complicated. So again, we're still in this notion of only circles to explain the motion of the planets. And we have, a planet orbit, such as that of Mars, but Mars itself is on an epicycle and maybe on another epicycle, and all these planets, all the known planets, had their system of epicycles with the Earth in the middle. So this was the geocentric view of the universe. The Earth was in the middle, no reason to think it was, and the sun was, orbiting the Earth, etc., and the planets all too. But so we had this incredibly complex system of epicycles. And at the end of the day, and the amazing thing is, this theory of epicycles, it lasted from Ptolemy's time, 3rd century AD, right up till the 16th century. And we had 1,500 years of epicycles. And as they grew more complicated with their observations, people were desperate to find maybe a cleaner solution to the problem. So this idea of having the Earth in the middle was also curiously epitomized by an English, he practiced many things, astrology, philosophy, he was a doctor as well, Robert Flood. And this is a famous drawing that he made depicting the symbol of not just the Earth, but man being at the center of the cosmos. And it's an interesting theme, which in some sense was way ahead of its time, because we've come in modern cosmology to believe that there is possibly some natural role of man, of an observer in the universe. In other words, there are so many universes that are possible according to modern theory. Most of them are not very good to allow planets to form, to allow life to develop, and so therefore there might be a connection between man and the universe, or it may be that we just haven't got the right theory yet, which is perhaps the most likely explanation. But it's interesting, this theme has come back to haunt us a lot since then. But let's now go back to how we finally got away from this very complex theory of epicycles. So Copernicus was the first genius who basically took a hard look at this, and he said it's so much easier if the sun is in the center, not the Earth. And then we can maybe imagine circular orbits. But even then it was realized the orbits simply, there were changes in brightnesses and apparent motion of the planets that could not be accommodated by simple circular orbits. So even in Copernicus' model, the sun was at the center, but he still had epicycles. And so that was not completely satisfactory, but it was the beginning of a revolution in which the Earth got displaced from the center. The Earth was now just one planet going around the sun. That was the great breakthrough of Copernicus. And it took two other astronomers at that time to finally push things a bit further. First, there was Tycho Brahe, who was the first person to realize that there were phenomena in the sky that were truly very distant. I mean, again, another tradition of Greek astronomy was the heavens were perfect, no changes. This was Aristotle's grand view of the universe. And Brahe really showed this could not be right because he saw exploding stars, we call them supernovae now, and comets, and was able to argue they had to be very distant indeed, and that therefore there were changes in the sky. And so Brahe also tried to have a simple model of the universe, but he couldn't get away from having the Earth in the middle and the sun and all the planets going around the Earth and the distant stars up here. And the whole picture only got finally clarified with the Copernican model basically gaining the day with Galileo, who was the first astronomer to use the newly discovered telescope at that time, a simple 2-inch telescope, diamond telescope. But he was able then to look at the moons of Jupiter. We call them the Galilean satellites, and there's beautiful sights in the sky, actually, with a small telescope. You see these 4 moons going around Jupiter. Clearly, they orbit Jupiter, and therefore Jupiter was the center of their motion. And so this finally was able to, this sort of argument was really the linchpin for heliocentric cosmology. But there was still something lacking, and that came with 2 more giant steps forward just after the time of Copernicus, actually. First of all, Kepler, Johannes Kepler, German astronomer, realized that the orbits were not circular. They were elliptical. And this, he measured this, the ellipticity of the orbits, and was able to demonstrate that, in one of the foci of the orbits, there was the sun sitting and the planets went in ellipses around this. And this could naturally explain the changes in brightness of the planets. They weren't going in circles, they were at different distances from the sun. And so that was the real step forward in astronomy. And then finally, sense was made of all this by Isaac Newton, who showed that the idea of ellipses was a natural consequence of the theory of gravity. And so in some sense, Newton was the father of the theory of gravity. It's a universal law that controlled the motion of the moon about the Earth, the planets about the sun, the Earth around the sun, etc. So that's where we then made the giant step to modern astronomy, really, with essentially the modern theory of the motions of the planets, thanks to Kepler, Newton, all the observations before. So let me tell you a little bit about the astronomy that was being done at that time. So what went into this astronomy were measuring very precise positions of stars. So this is before the age of the telescopes, first developed in the 16th century. There were observatories all over the world, actually, designed with astronomers to record the positions of stars. This was very important because they were able to use their knowledge of stellar positions it was very interesting for astrology at the time. Many of the astronomers of those days were astrologers. Astronomers were astrologers. It was indistinguishable. And one of the great things they were able to predict, for example, going back even earlier than the Greeks, was by many of these observations of stars and records of the exact displacements of stars over time and and motions of the sun, etc. They could even infer, because there was a slight precession in the axis of the Earth that was measured by studying positions of stars. And so they could actually predict eclipses. That was one of the great discoveries. And if you could predict an eclipse of the sun, that was an incredibly powerful thing a long time ago for astronomers to suddenly say the sky would go dark for a certain hour. This was immense power. And so astronomers certainly had a very privileged role in society. And this shows you some of the observatories. There's the oldest one, actually, that is still more or less in existence, is in Korea, actually, built in the 17th century. Here's one from Chichen Itza, the main observatory. And again, these were just used to record positions of stars, basically, looking through these, and in China. And there are slightly more modern versions of these too. This is a famous one which many may have seen in Jaipur, where again these various devices were used to note positions of stars in the sky and chart out the motions of the planets, etc. And so this was how astronomy got to be precise. Before you really used telescopes. And okay, but then along came the telescopes. And so there were 2 key things that modern astronomy had to develop. The idea of distance. They had to show that stars were truly very, very far away. Now, as the Earth goes around the sun, you change your position, and so if the star is not that far away, its apparent position will change. We call this parallax. right? You look at it from different perspectives. But if the star is truly distant, okay, then the parallax gets smaller and smaller. And so if you can measure this parallax, then just from your baseline, the Earth's orbit around the sun, just as you do in architecture to measure, you can measure mountain heights or skyscrapers, whatever, by parallax as well. Same idea is used to measure chart stars. And Friedrich Bessel, German astronomer, was the first to do this. And he chose a star that was about 10 light years away and deduced that distance, 10 light years, because it displaced its position by a small amount over the course of 12 months. Okay, over the course of the year. So that began our real understanding that stars were truly distant, and there had to be some phenomenal scale associated with the distant stars that we could only discover later, really, as we built bigger and bigger telescopes. And so the ultimate goal this led to was a satellite that was actually just launched a couple of years ago called Gaia. And this satellite had high precision measurement of stellar positions. This picture shows you 1 billion stars, which this satellite mapped. But it was able to measure the position so precisely that it could actually measure parallaxes for vast numbers of these stars and prove they really were not just 10 light years away, but many of them were hundreds and thousands of light years away. This was really measuring for the first time, mapping out the galaxy in extraordinary precision. We knew about that from earlier stuff, but this really was high precision parallax astronomy to perfection. 1 billion stars, all distanced from this satellite. Okay, so there's one other important question about a star. I mean, its size, the size of a single star. And so we'd conjectured that stars are pretty big. I mean, we can measure, we know how far away the sun is, we can see its size. It's, 100,000, nearly 1 million kilometers actually in radius. But what about distant stars? We'd love to prove they really were enormous balls of fire, basically. And so this was another breakthrough, this one in the early years of the 20th century, due to an interesting combination of an English astronomer who was a theoretician, Arthur Eddington, and an American physicist who was very interested in building devices that could use light beams to interfere with each other. Lights are waves, you get peaks and troughs in the light beams, and if two different light beams can actually interfere and give you an intensity increase, then you can use that to measure the size of the system from which they're coming, essentially the radius of a star. And so Michelson chose a nearby star. This is a picture of Betelgeuse, it's a beautiful star. It's an Orion. It's the bottom right-hand star in Orion. It's a red giant star. We've inferred for a long time it's very big, but to actually directly measure the size for the first time was a great achievement. And that was done in 1920, actually, thanks to the calculations of Arthur Eddington, in which he actually figured this out, how big the size had to be, and that it was feasible for Michelson's experiment to measure it. And this shows you the experiment that he built. It went on one of the largest telescopes at that time in the world, a 60-inch on Mount Wilson. And it was a device on the top of this telescope with a couple of mirrors. And the mirrors basically combined light from different slightly different regions of where the star would be, and showed you that the light beams would interfere or not, and that could therefore give you a measure of the size of the intrinsic star far away. And so that was a great breakthrough that was made in 1920 or thereabouts. Okay, and this, of course, did get immense headlines at the time. This is the New York Times from 1920. You could see a giant star equal to 27 million suns like ours was the headline. So it was a great achievement to finally prove that stars were intrinsically huge things. And of course, the fate of the sun will be, to become a red giant, just like Betelgeuse. And it will become so big that the sun will swell from its 1 million kilometers up to maybe 1,000 times bigger, or 100,000 times bigger, and completely overtake the orbit of the Earth, and the Earth will be burnt to a crisp. This won't happen, fortunately, for about 4 billion years, so we have some time to prepare for that. But you know, it's maybe the ultimate version of climate warming, right? Which we will presumably have to leave the planet by then, and we'll be able to, no doubt. Okay, let me just tell you another historical development in astronomy that's fascinating when you look back at it. So there was a big debate that went on in the 20th century, the early years, as to whether it was more important to do detailed observations in surveys of counting many stars with smallish telescopes, because you could do accurate work with those, or whether you should put and hire people to do this work, or whether you should try to look for a genius who would make use of a really big telescope and look further than anyone else. And so it was the question of, do you do your work collectively, or do you foster the environment for an individual to make a huge step forward? And there was a debate that went on. It still goes on today, just how you plan your strategy for making new discoveries. So Pickering was one of the people who was very much the traditional astronomer of the time. He argued that you actually have to have the kind of work to be done more than other. It much depends on other conditions. The man behind the gun, actually it was more the woman behind the gun, I'll show you that in a second. But he was arguing that, do you need a huge battleship? Maybe, this is 1909, the biggest telescope then was 60 inches in diameter. Why would you ever want to build a bigger one? You just do your work with the smaller ones. Well, other people did have a very different approach to philosophy, and the main person who disagreed with it was George Ellery Hale. And so Pickering was at Harvard, director of the Harvard Observatory. Hale eventually went from Chicago to California and founded what became known as the Carnegie Observatories, which hosted the world's largest telescopes for many years. And so he believed that, for example, that you should encourage individual initiative. And it's interesting that here is Pickering's philosophy carried out in practice, where he said that you have to have many individual researchers who are not paid much. In this case, they were most all women, and he used them to do the tedious work of counting stars with smaller telescopes. And he was able, therefore, to set out the scale of the galaxy, etc., etc. But it was Hale who wanted to look beyond this and look for the distant things much, much further away. And there was a different philosophy that went on about whether you wait for the individual who will lead the way with something very big and incredibly expensive, or you do your work very detailed and conscientiously with in the way that Pickering developed it. And in fact, Pickering's assistants, these are them, they made immense discoveries of great importance for charting out the Milky Way. But to go beyond that took a much bigger telescope. And so it's interesting that came about because of private philanthropy. So these were the days when, if you wanted a big telescope, actually the same is true now, a really big telescope, it's hard to persuade your government just to put the money into that. Now, at the time, there were some early 20th century, that there were some philanthropists who really had great visions of the universe. And maybe the one that George Ellery Hale, made closest contact with was Andrew Carnegie. And he was able to persuade Carnegie to fund first a 100-inch telescope on Mount Wilson, and then eventually the 200-inch, the world's largest for many years, on Mount Palomar. And it was with these telescopes that we first actually measured the scale of the universe and how vast the cosmos is. So it made a huge difference, these big telescopes. And again, the contrast is Galileo. He had a 2-inch telescope. So you see this this intriguing painting showing, made many years later, of course, but showing Galileo illustrating to the in Venice what one could look at with a small telescope. Okay, so but from 2 inches, we've gone incredibly far beyond that. So here's Galileo's telescope, 2-inch diameter. It's got a magnification power, which is, factor of tens, hundreds, but it's nothing compared to the huge magnification you get with a much bigger diameter lens. And so where do we go with these bigger telescopes? Well, the next step, the major step was actually made by another philanthropist or private individual, the Earl of Ross, who in Ireland actually was fascinated by astronomy, and he built what for more than half a century was the world's largest telescope, 72-inch diameter telescope. Then on Mount Wilson, they soon were able to in the 20th century, were able to go beyond this, the 100-inch, then the 200-inch in 1949. And the latest developments are the following, that we're now getting beyond the ability of telescopes that are just meters across, 3 meters, 5 meters, to telescopes now that are many more meters. So the largest one in the world will be either 30 meters or 39 meters. There are two different projects actually. The 30-meter telescope is an American project, again partly financed privately through the Moore Foundation, but partly by many countries involved as well. And that has been struggling to get started on Mauna Kea because of resistance from the local inhabitants. Mauna Kea, this volcano with a site with many, many telescopes actually is partly a sacred site. But finally, they seem to have overcome the resistance, which considered of people lying down the road to stop construction trucks getting up to the top. Anyway, all that seems to have been resolved with various court cases, etc. And so that is on track now to be built 30 meters across in 2027. Meanwhile, in Europe, this one is purely European funded. It's one of the big advantages of being in Europe, of course, that we have so many countries there that can put vast amounts of money into science. And the Europeans are building a 39-meter telescope, and the UK is part of this project, to be completed in 2025 on a high peak at the Atacama Desert, some 17,000 feet altitude actually in Chile. So that is the immediate future. Let's go back to the Earl of Ross. So this was his 72-inch telescope, which was built in Ireland in the 19th century. And with this, he was able to chart out, look at many distant nebulae. We didn't know they were intrinsic galaxies. They were called island universes. People speculated they might be as big as the Milky Way or not. But he was able to look at many of these. And this was in the days when cameras were not really available. They had not been designed to work with telescopes like this. So all that one could do was make sketches of what you saw through this telescope. And so and then after the 19th century, 1949, skip forward half a century, then we come to the 200-inch Mount Palomar, constructed in 1949, which from then up till a few years ago was the largest in the world. And then there was a European project using, this was a 5-meter telescope, there was an 8-meter European project called the Very Large Telescope, and which was built roughly a decade ago in Chile, and now there'll be even larger ones in the near future, in the next decade, coming along. So all of this is very, very dramatic. What happens after that? Well, here I'll show you the 30-meter telescope, the design for that. This is the one going on Mauna Kea. It's hard to imagine the scale of this. Here is, I think, a truck over here to give you some feeling for this. Okay, and so there's that's the mirror, and with a focal plane behind it to attract the light. And here is the 39-meter telescope, again an architectural design to be finished in 2025. They've already begun clearing the site and started the basic construction. And again, you have to just try to get some feeling for the human scale relative to that. Okay, so. Okay, I want to now show you the different sizes of these telescopes, actually. So let's just look at the relative scale of things. So actually, This is over here in the center, the 30-meter telescope. And these are other ones that have been built over the past, and this will be the 39-meter. So these are the two big ones for the future, and these are other ones from currently existing. And this is another future one. This one will be some 20 meters across. But all these other ones are existing ones, and these two actually are under construction now. But to give you a better feeling for the size of these telescopes, here is the Colosseum, right? Okay, and so you can see now we are really making these incredible monuments on high mountain peaks, basically, to look at the sky. So it's clearly we're reaching the limit of what we can do from the Earth, but this is about as far as we can go. Remember, the Earth's atmosphere is a big worry, so you have to think of clever ways to work your way around, the atmospheric turbulence to give you fluctuations of images, things like that. So none of that is simple to do. Let's go back to the Earl of Rosse. So this was a sketch he made in 1845 of a nearby galaxy. And here is the galaxy as seen by the Hubble Space Telescope. Okay, so you can see the Earl of Rosse got it pretty much correct. He could clearly see the spiral arms. He could see the satellite galaxy over there, which is a neighbor and probably eventually falling into this one. But it's just amazing all the detail you can see with a big telescope. For example, you can see all these individual stars, or clusters of stars actually. Each of these red dots are clusters of some hundreds of thousands of stars. You can't quite resolve the individual stars, and all of this stuff in the center is many stars so close together you can't even see individual ones. But anyway, all of this Earl of Rosse got a pretty good picture of. But it was not until we got observations like this that we could really appreciate the grand scale of things in the universe. So it's one thing to do this the classical way with just with the human eye, but it was just amazing how much further one can go with modern technology. And in fact, CCDs, which we are used to make these images, were invented for astronomy actually originally, because the astronomers needed some incredibly sensitive device to work in the dark, and they were commercialized for all of our pocket cameras, etc., mobile telephones. So that was an interesting story in itself of the interface between commercial activity and science. It was an amazing spin-off, actually. So that's the story for the optical part. As I said, the Earth's atmosphere is a worry. One has to go into space to get the ultimately sharp images. But one other thing you can do from the Earth is do radio astronomy. So it turns out that we're biased with the human eye. We see, at a certain narrow range of wavelengths, but objects in the universe don't have this bias. So they actually emit light, radio waves. And now these radio waves, it's not as though we're getting a television channel or anything from distant objects, but something like a massive black hole in the universe will actually undergo explosions and will emit radio signals just because it heats up plasma to some high temperature. There's high magnetic fields made around these very strange objects. And you get radio phenomena which give you a whole different view of the universe. The high energy universe, we call it, the very active universe, full of black holes and related things, and maybe dying stars, all sorts of things that are very important for radio. Okay, so here is one of the giant radio dishes that was built quite a number of years ago, 300 foot across in West Virginia. This, interestingly, had a slight problem of metal fatigue. So you can see it collapsed just overnight. They were just, they came back the next morning and there it was. But thanks to the powerful politics of the senator in West Virginia, they were able to construct a new one, within a decade or so, and this is the current 300-foot diameter greenback radio telescope used for mapping the sky and getting radio waves, focusing them with its curvature and studying what the radio universe is made of. Well, the bigger the telescope, the more resolving power you have. So why would you stop at 300 meters? Apart from metal fatigue, okay? But how do you get around metal fatigue? Well, there's a very clever approach to that. You go to a huge crater, okay? And in the crater, a natural crater on the Earth, you can lay out your radio telescope. And so this has been done in Puerto Rico, Arecibo, Puerto Rico. And so this is 300 meters now. The first one was 300 feet. This is 3 times larger. The greenback one would be roughly this size. 300 meters, and there are cables that span the focal point. It's over here. That's where you put the camera, the receiver, to see the radio waves focused. So that's, and although obviously the crater, you can't steer the crater, what you can do is you can juggle the focal plane a little bit, but as the Earth goes around the sky, then you see different bits of the sky. So basically that's how you do radio astronomy with such big non-movable dishes. The ones I showed you before were steerable radio dishes, this one is not. So that currently has been superseded by this telescope in China, just finished a couple of years ago, and this one is 500 meters across. So it's, again, a similar idea. They've covered the basis of this crater with metal plates, and this gives you a huge receiver, and they have these system pylons with cables which suspend a focal, the receivers in the center to collect all the information from that. So that is where things are going in this field. In space, we have a whole other approach. Okay, here it's not so much size that counts, but it's the ability to go into distant parts of space away from the Earth, so you can reduce the light from the Earth and get a very dark sky. There's no Earth's atmosphere, so you don't have the twinkling of stars. So this is great for doing astronomy. And not only optical astronomy, but it's also a fact that X-rays, I mentioned the radio universe, radio waves get to the Earth, but X-rays do not. They're blocked by the Earth's atmosphere, fortunately for us, but there are many X-rays coming from space, from the sun, for example, from many stars, and from many of these black holes that do violent things, violent explosions, that are a very important part of the universe. We have one big black hole at the center of the Milky Way, for example, weighs something like 1 million times the mass of the sun, and there are other galaxies with similar ones to them, even bigger ones. And they emit X-rays in profusion, and we can only study them by going into space, okay, because there's no atmosphere to block them from us. So that's the motivation behind developing telescopes in space. First, the Hubble telescope, which looks in the optical and the ultraviolet, a little bit in the infrared, has been going now for nearly 30 years actually, and it's just a 2-meter telescope, rather small, but because of the incredible clear visibility in space, it has given us these beautiful images. I showed you one of the Whirlpool galaxy just now. Okay, one can also look for infrared. Again, infrared light is mostly blocked, again, by the Earth's atmosphere, by water vapor. It absorbs infrared from far away. That, in fact, is the cause of the greenhouse effect. The Earth's atmosphere actually will absorb infrared and lead to a slightly more warmer climate on the Earth. But the infrared, if you like to say, you have to go to space for. So you have to go above the atmosphere. And so here's one telescope, which is 3.5 meters, launched 2009, no longer working now, but it worked for nearly a decade, taking beautiful infrared images of the sky. And then X-ray telescopes. We're in this new era now where we look for X-rays in space. And so this one is just a meter or so across, but it's enough to give you this view of the sky unparalleled that you can't see from the Earth. And by clever technology, you can even focus the X-rays and make images of X-ray objects, X-ray nebulae, X-ray explosions that are as good as optical images in terms of their resolution and their clarity. And so we're learning much about the building blocks of the universe far away from all these wonderful types of telescopes. So the conclusion recently of a lot of this is to go to a part of the universe nearby where it's even darker than anywhere in space, actually, from certain points of view. And this is the far side of the moon. So why would you want to go to the far side of the moon? It turns out that radio waves of very, very low frequency are an interesting way to study the dark ages of the universe. Why the dark ages? Well, that's before there were any galaxies, before there were any stars. And the problem with studying this epoch of the past is that the radio waves are so stretched out, they go to very, very low frequency, and these also are blocked on the Earth. They don't get through to the Earth's observatories very well. And in space, just going anywhere in space is not necessarily the best thing to do, because the Earth is a huge transmitter of radio waves, thanks to all our TV stations, whatever. But if you go to the far side of the moon, there you're blocked completely from the Earth. And that is potentially a wonderful site to study the dark ages from. So the pioneer in this field is the Chinese Space Agency, and just a month ago they launched a probe that is now sitting on the far side of the moon, the first ever probe to land on the far side of the moon. And you can see these radio antennae. That is this low frequency telescope that will be taking data from the distant universes and trying to study what happened before there were any structures. The Chinese did this particular project in a great hurry. It turns out that their system in this construction they landed was not engineered to give you really, really low radio backgrounds. But this was a pilot version, and they're hoping now in the next few years to launch much more sophisticated versions of these telescopes to maybe orbit the moon and land on the far side, etc., to do this search. And I'm sure other countries will be doing that too as well in the not too distant future as well. But that's one future for a whole new type of astronomy. Okay, so now let's go back to another type of astronomy, which is sort of mind-blowing, really. The sun produces energy by thermonuclear fusion, by burning hydrogen to helium. That accounts for the wonderful way we have energy to solar energy, etc., to be able for the Earth to survive and develop life, etc. But when this energy is made in the middle of the sun, there is, we'd like to prove this is how it happened by thermonuclear reactions. And we can study these reactions in the middle of the sun from neutrinos, these tiny, tiny particles that can travel through anything. They're very weak interacting, but they're producing nuclear reactions. They will come to the Earth, and you can actually measure them in principle and figure out what is going on in the middle of the sun. So that it really is a thermonuclear reactor, which is a great source of energy and heat. And so here's an example of such a neutrino telescope. So it's a huge cavern under a mountain, a disused Japanese mine, filled with highly purified water, about 10 meters or so above the surface. And you can see the engineers are going around inspecting all the phototubes, which are above there. And so these are phototubes designed to look for light flashes that are produced when neutrinos from the sun interact with the water and give you very tiny light flashes that last a nanosecond. But this happens because the sun has so many neutrinos. It's a rare event, but every now and then they should see something. And what is fascinating is this. We know these neutrinos are produced in the Earth's atmosphere, right? So they come from, let's say, cosmic rays. But those come from above. But if you can look from below, things coming through the Earth, then only the sun could have produced those. The Earth's atmosphere would not be making those. And the sun makes them because the sun's neutrinos hit the Earth's rock, and they produce particles which can give you light flashes in the water. So it's an indirect consequence of neutrinos. It's not direct neutrinos, but the tiny muons the neutrinos make in the Earth's rock that can be seen in principle. And so that's one experiment. Here's another one that does the same thing. And this one is in an even more exotic place. It's at the South Pole. And at the South Pole, they've managed to drill, using hot water, strings of electrically connected phototubes, which are spaced, to be hundreds of meters or more apart, to instrument basically a whole kilometer of ice. You have to go very, very deep because you want to be very, very dark. Okay, and they basically, to give you some feeling for the scale of this, this is the scale of the Eiffel Tower over there, and on the right. And so we're talking now about something that's about 2.5 kilometers basically. And in this video on the right, you can see how they can use this as a telescope, because the neutrinos, basically, if they come from some point in the sky, from the sun, for example, they traverse these strings at slightly different angles, so you can infer the direction they're coming from. And so this really is a gigantic telescope. By looking underground, deep down, you can actually, in principle, see the sun producing neutrinos, which hit the Earth, create muons, which give you these tiny light flashes, which are registered by these phototubes. So it's, again, mind-blowing astronomy, and it's a kilometer-sized telescope, basically, designed to look for neutrinos from the sun, and eventually from black holes in the universe, from other things out there too. But the sun is the nearest and brightest source to start with. Okay, and just continuing with this theme of interesting things out there in the universe, I mentioned cosmic rays, right? So cosmic rays are particles which are like protons, basically, but produced at really high energy in explosions in the universe, probably by massive black holes. And so we're bombarded by cosmic rays on the Earth. Again, the Earth's atmosphere basically protects us from these. If you live at high altitude or fly a lot, you'll get a little more bombardment by cosmic rays. It won't be fatal, it won't even be dangerous. It's only when you go into space for a long time that cosmic ray bombardment is thought to be a serious issue. If you were to spend 9 months in a rocket ship going to Mars, it's been predicted that by the time your astronauts got there, they'll be riddled with cancer, they'll be half blind, etc., because of cosmic ray bombardment. And you couldn't put enough lead around that rocket ship to shield you properly because it would be so heavy. So that's a big problem for the future in exploration of Mars. Anyway, to come back to the Earth, then we can detect these cosmic rays by a very clever trick, because they hit the Earth's atmosphere and they disintegrate. And basically they give you what is called an air shower of many low-energy cosmic rays that give you light flashes, again, in the Earth's atmosphere from decaying particles. So we're looking for these air showers, which last nanoseconds too. You can basically try to figure out how many cosmic rays are hitting the Earth's atmosphere. And so we're beginning to do some of that. So this shows you what an air shower is. You have some event coming in at the top, a high-energy cosmic ray, triggering lots of other interactions, and then each of these interactions will produce a slight flash of light, and you can map them out by having many telescopes. So these are weird telescopes. Again, these are tanks of highly purified water, okay, which are used, again, to detect these light flashes, as in the other experiments I showed you. And in this case, they're spread over a huge area in the Argentinian Pampas for the world's largest high-energy cosmic ray telescope. And so we're now discussing something like 1,600 of these tanks, each one with 60,000 gallons of purified water spread over 1,200 miles, each 1.5 kilometers apart. And they are basically monitoring. You need a huge area because there are so few of these particles, and the air showers spread out over a large area. So that's how you see them. We're learning all about the cosmic rays out there in the universe. And again, this is like a telescope, because you can see where these are coming from in the sky once you start seeing them. We're still beginning to do that now, but this is one of another most amazing telescopes. Okay, so let me now end with telling you another interesting goal for telescopes. That is the search for life in the universe. So the person who had an immense impact on this field was a wealthy Bostonian called Percival Lowell, who went on to found his own observatory in Arizona. And again, this was the days before you had cameras, really, very effective ones anyway. And he was able to, and he looked at Mars. And he made sketches of what he saw on Mars. And what he sketched were, this is one of his diagrams. And so these are the canals on Mars that he thought he saw. Now, partly this was a misinterpretation of an Italian astronomer called Schiaparelli, who talked about canali on Mars, but in translation, the word canali in Italian, I am told, does not directly mean canals. It just means channels, okay? But you can reinterpret it as canals, and this is what Lowell did, and went on to draw his own maps of the canals he thought he saw on Mars. And so this was thought to be a huge canal network, according to Lowell. And he went on to write articles in the early years of the 20th century. This is from New York Times 1907. Mars is inhabited, says Professor Lowell, the abode of intelligent constructed life, based on these canals. And he went on to observe them, and amazingly, there were even changes in the canals that he thought he saw from one year to the next. This was another headline from the New York Times: Martians built 2 immense canals in 2 years. Okay, so, this is the Italian who discovered these canali in the first place, Schiaparelli. So, of course, we know this is all wrong, right? Why do we know this? Well, here are the modern pictures of Mars. Okay, so you can see there are funny markings on the surface of Mars, which, especially if your eyesight is not perfect, maybe, or with a bit of imagination, maybe you can start drawing canals. And certainly, when we have these beautiful images now from the Mars, one of the Mars missions, you can see it's a rocky landscape with no particular evidence of any, anything not just totally natural on there. However, this is, where we are with Mars, but why not? Mars is a pretty dead planet. Maybe if we dig deep on Mars, we might find something interesting. That's one of the goals of future exploration on the surface. It's pretty arid, maybe with ice caps at the North Pole, but not much more. But we would like to do a little better. And so I'm going to end by telling you about one of the most amazing future projects, which is actually to try to image distant planets. So to take images of them, so not just planets in the solar system now, but planets around nearby stars. And if you can image enough of these distant planets, we call them exoplanets, then maybe at night you'd see the cities light up or something, if there were cities, right, that sort of thing. Or look for evidence of anything interesting that might, go beyond Lowell's canals on Mars. So this is a project that totally futuristic, but it's the sort of direction that we need to go in if we ever want to do this. You go to a crater on the moon, and so you choose a crater near the South Pole or the North Pole. There are many craters in the South Pole, because near the poles, the sun never gets very high above the sky or very low. So it's always temperate climate. If you're near the equator of the moon, it gets incredibly hot midday, incredibly cold at night. But near the equator, it's much more moderate. And there are these craters, enormous craters actually, which are perpetually dark. They're so deep, and because they're near the poles of the moon, the sun never gets high enough to light them up. So they're great places to put your telescopes, especially when looking in the infrared. And there's one of these in particular with very high rims, so it's perpetually illuminated by the sun. Actually, even at midnight, the rims are high enough, and it's near the rim of the moon. There's some sunlight which gives you solar power. So that's the idea. And here is an artist, and the idea then is you'd instrument this crater with a series with many mirror segments, and it's a bit like, remember the Arecibo thing I showed you in radio astronomy? This is now infrared astronomy or optical astronomy. You can do the same thing in principle with no Earth's atmosphere to bother you, to make the temperature, the telescope beams, to mess them up with turbulence. And so the idea is you can instrument this whole crater and focus the light, having a big cable with receptors in the focal plane, and use this then to image distant exoplanets. And because this is so big, this is many kilometers across, you have the resolving power. And so this is the hope, and then artist conception. You can go to, let's say, a wonderful system like TRAPPIST-1, discovered in the past couple of years, which has a whole number of planets orbiting it, and that'd be a great place to do imaging. This is the quality of the image that, in principle, this telescope could get. And it's 40 light years away, and there are enough of these exoplanets within that distance to give us an interesting, goal to search for.
Obviously, there's no guarantee you'll ever find anything, but if you do, it'd be amazing, of course. So that this is one of the major goals of modern astronomy, to build telescopes large enough that one can have some hope of looking for indications of distant life in the solar system. So maybe that'll come, maybe it won't. If we find nothing, that'll be amazing too, if you look at enough planets. So either way, we can't lose, and it's a great focus of modern astronomy. So thank you.